Good afternoon, everybody, and welcome to the afternoon session, so the sixth section and the last one of today. We will have four speakers talking about, in general, molecules and one about semiconductors. So in the order, the first one will be Françoise Remacle, then we have Janaky, Kasra Amini, and the last one will be Küpper. So I would like to remind you the time for the speakers. So the first one is, it will take 35 plus 5 minutes of question and answer, and all the other invited talks instead will be 25 plus 5 minutes of question. I would like to remind you to use the Q&A application to write the questions, so I can actually right away ask directly to the speaker. And I would like also to remind, in case there is no more time for further question, to use at the end of the session or the entire session the meet the speaker opportunity. And so with that, I would like to start with the first speaker of this afternoon, Françoise Remacle, presenting ultrafast vibronic and photoelectron dynamics in molecules, both excited by short femtosecond pulses. And I leave the floor to Françoise.
Hello, you can hear me?
Yes, clear.
Good afternoon. And like most speakers, I would like first to thank the organizers. It is a very nice meeting in spite of the unusual circumstances. So I will report on our recent progress on simulating ultrafast vibronic dynamics in molecules excited by short femtosecond or attosecond pulses. Before I really begin the talk, I would like to thank my collaborators at the University of Liège, Alessio, Caio, and Stefan, and our long-term collaborators at the Hebrew University, Professor Rafael Levin and Ksenia Komarova. This is also something speakers before me have already stressed, that it is interesting to excite and probe molecular dynamics with atto and few femtosecond, few cycle pulses, essentially for two reasons. The first one is that one can address and probe electronic motion in molecules on its intrinsic timescale, which is really a sub-femtosecond timescale. But also the second advantage is that because the pulses have a short duration, they have a broad bandwidth in energy, and therefore, since in general in polyatomic molecules we have a high density of electronic state, a few eV above electron state, exciting a molecule with such pulses allows to build coherent superposition of several electronic states. It allows really to create, with the initial excitation, a non-equilibrium electronic density, which can be tailored by the parameters of the exciting pulse, its carrier frequency, its polarization, its carrier envelope phase, and also, of course, its duration. And in this talk, I will show example how we can create and steer the different initial state and steer the nuclear dynamics by adjusting the carrier frequency, the polarization, and the carrier envelope phase in different kinds of molecular systems. So this is really our long-term goal, is to understand how to tailor the initial non-equilibrium electronic density to drive the motion of the nuclei to specific products. And this is a very challenging aim, because as we all know, chemical reaction imply a change in the configuration of the nuclei, and I show here the nuclear rearrangement that is induced by ring closure of 4 carbon in a 4 carbon reaction. This is the photo isomerization of norbornadiene into quadricyclane. This is an example that I will discuss more in the rest of the talk, and therefore the nuclei need to move, which means that the timescale for chemistry is the timescale for nuclear motion. And typically we make the Born-Oppenheimer separation. We suppose that we can define potential energy surface. This is a cartoon here of the first and excited state of norbornadiene, and here the ground state. And we assume that the electron adjusts instantaneously to the position of the nuclei. And typically, in mechanism for control, in femtochemistry, where the pulses are longer than the kind of pulses we are talking about in this meeting, you will excite a single electronic state, and then the vibrational wave packet on the excited state will start to move, and driven by nuclear motion, you will get a change in the configuration of the electrons, and you can go to the product here, quadricyclane, or go back to the reactant, which is the open form here, norbornadiene. And so the point is that if we now excite the system, and here it is a slide on LIH, but the situation in norbornadiene is rather similar. If we excite such a system with a short pulse, we are going to build a superposition of several electronic states. So to start with, we have a coherent superposition of states before the onset of the nuclear motion. When the nuclei start to move, they will also encounter the coupling between electronic states that is induced by the nuclear motion, and therefore there will be a redistribution of the amplitude between the different electronic states until the wave packet goes to the product of the reaction. And so really the question is, can we exploit the features of the initial non-equilibrium density to control the reaction and the yield in the different products? So to understand the role of this electronic coherence in the reactivity, one needs to adopt a fully quantum approach to compute the electron nuclear dynamics. And what we do is to solve the time-dependent Schrödinger equation on the grid. And we face the challenges that have also been listed in previous talk. We need to take into account several electronic states. We need ideally to have accurate values for the transition dipole between these states, for the non-adiabatic coupling between this electronic state, and also if the system can photoionize, we need to include photoionization matrix elements. We need to include the pump and the probe pulses in the Hamiltonian that governs the dynamics, and also we need to compute this dynamics is in as many nuclear degrees of freedom as we can afford from a computational point of view. So we have implemented two ways to kind of speed up the computation, and also that allows us to include more degrees of freedom. We are computing the momentum and the kinetic energy on the grid using a finite different algorithm, and it allows us to save quite a significant amount of computational time. And we also have developed a method, an efficient method to compute the photoionization matrix element, because we will need them for each configuration of the nuclei that is accounted for in the grid that we are using. So we solve the time-dependent Schrödinger equation. We include the coupling to the photoionization continua, so we solve it using the partitioning technique, meaning that we have a system of coupled differential equation, as is shown here, that we have dynamics in the bound subspace, we have dynamics in the continuum subspace, and we have the coupling between the two subspace, which is due to the photoionization matrix element. So our wave function will have amplitudes on the state of the neutral, several electronic state and several grid point, and also amplitude on the state of the photoelectron and of the state of the cation, which means that we have a huge vector, typically millions of complex amplitude that we need to compute as a function of time using this system of equation. So this is here the system. I forgot to put my screen in full screen, so here it is now. So this is the matrix that we are using to solve this system. As I already said, we include in the bound subspace the coupling to the photoexciting pulse, and in the dipole approximation, we include the non-adiabatic couplings between the electronic state. For the continuous subspace, we assume that we have a separable Hamiltonian. So we have the part of the cation that is computed for several electronic states in principle at every grid point. And we have here the Hamiltonian of the photoelectron, and we take into account the dipole coupling. Here we have on the off-diagonal element the photoionization matrix element, and the way we speed up the computation is to go back to the expression of the Dyson orbital in terms of atomic orbitals, which in quantum chemistry are Gaussian function, which allows to write this matrix element really as Fourier transform or derivative of Fourier transform, because we are using, to discretize the continuum, we are using a set of orthogonalized plane waves. So we are working in the single active electron approximation. We can not do much more in view of the fact that we need to compute this matrix element for every grid point in the grid. So we set up this method to study the photoionization and photoexcitation of the lithium hydride molecule, a simple diatomic molecule. And as I said, we typically have to propagate about 7 million of complex coefficient to do this computation. We use a short few cycle IR pulse to excite the neutral LIH molecule to the first, the second, the third, and the fourth, essentially, excited state in this green region here that is shown on the potential energy curve. And we need to set up this computation, the permanent dipole, the transition dipoles, and also, of course, the NAC coupling as a function of the interatomic distance. I want to note it here because this is a feature that we exploit for control. These are the curve of the permanent dipole of LIH, of the different excited state, and you can see that they are of alternating polarity. Some of them are positive, others are negative, and the positive one, which means that we have a dipole moment that points to the lithium atom, so it is Li plus H minus, are those of the ground state, of the second excited state, and of the fourth excited state. And the first excited state and the third one has the opposite polarity. This polarity character actually corresponds to a charge transfer character that is transferred to the higher and higher electronic states that, as you can see here, there is a 1/r curve as a function of the stretching of the internuclear distance. These are the results of the early time dynamics, the dynamics that occurs during the excitation by an essentially 2-cycle IR pulse, 720 nanometer for the carrier frequency. And this is the transient dynamics that we get for a carrier envelope phase that is of the pulse that is equal to 0, meaning that the maximum of the field is pointing to the lithium atom. And this is the dynamics that we get from the exciting the system with a pulse that has a carrier frequency equal pi. And then we have the maximum of the electric fields that points, to the negative Z direction, which is the hydrogen atom. So you see that we have a kind of rich and complex transient dynamics. We see that the bulk of photoionization here occurs when the field is maximum. And we also see the effect of the polarity of the different excited state, because we essentially excite the negative polarity state, that is sigma 1, when the field is negative, and the positive polarity states, which are sigma 2 and sigma 4, when the state, the field is positive. Which means that in the second half of the pulse, we get less photoionization, and there we get a selectivity in the population of the different excited state. This selectivity is summarized here in this table. You see that with the CP phase equals 0, we essentially populate the sigma 1 state and sigma 3 and sigma 4, while with CP equal pi, we essentially populate the sigma 2 state and the end of the pulse. And then the question is if this initial selectivity survives the fact that now the vibronic wave packet will go through the two NAC regions when the molecule is going to the fragmentation channels. We have a NAC region just at the exit of the Frank-Condon region, and we have a second NAC region on the way to the fragmentation channels. And so you see that we essentially keep the selectivity that was produced by the CP control of the pulse. We do see that when the wave packet is going through the NAC region, we have transfer of amplitude between the different electronic states, but at the end of the NAC region, we recover the ratio, or a modified ratio, but essentially the same ratio, in the sense that the dominant state is the same after the NAC region as it was before. And this is true for this dynamics, for the CP equals 0, and also for the CP equal pi. We maintain that we essentially have sigma 1, sigma 4, and sigma 3 for CP equals 0, and sigma 2 for CP equal pi. So this is a complex slide, and I will not explain all the details, but it is to show that in spite of the fact that the vibronic wave packet is going through strong NAC coupling on the way to the fragmentation channels, we maintain the phase relation in the coherence between the electronic state that was imprinted by the carrier envelope phase of the exciting pulse. This is the coherence sigma 2, sigma 3 as a function of the internuclear distance and as a function of time. And you see that it is beating all the way to large internuclear distance with a frequency that is dictated by the energy difference between these two electronic states. Right after the excitation, the coherence for the CP equals 0 dynamics has an opposite phase that it has for the CP equal pi. Then it goes through the NAC region, and then we observe a branching of the coherence with the lower part that remains, that is brought out of phase, and the upper part of the coherence, that is this part, that remains in phase. And the same branching is occurring also when you go through the second NAC region. So just the next point, the last point that I want to mention about LIH is that we also studied in collaboration with Rafael Levin and Ksenia Komarova at the Hebrew University how the isotope effect in LIH, so looking at LID and at LIT, will affect the amplitude exchange and the efficiency of the NAC coupling as the vibronic wave packet goes, as a coherent superposition of state, goes through the different NAC region in this molecule. So now I would like to go to a larger system, so to the three-dimensional quantum dynamics of the photoisomerization of the norbornadiene molecule. So the four-center ring closure that goes to a quadricycline upon UV excitation of the norbornadiene. In order to implement a full quantum study, we had to reduce the dimensionality for the motion of the nuclei, and we chose to freeze the C3H2 bridge, this bridge, and to describe the dynamics of the 4 carbon and the 4 hydrogen using 3 reduced coordinates, which are shown here. They are essentially the CC bending, the ethylene stretching, and a distortion of the symmetry of the C2V symmetry of the 4 centering that allows us to describe correctly the distortion necessary to go through the S0, S1 conical intersection that brings then population into the norbornadiene web. So here too, we need to compute potential dipoles NAC. We do it at the CAS average level. We have using OpenMolCAS. Alessio Valentini is a developer of this program. We have 65,000 grid points per electronic state. We do it for 14 electronic states, but we retain only the 8 lowest state in the dynamics. You have a cut in the impair surface here along the theta coordinate. You have here a 3D view where are the important geometries for the dynamics. We get a reasonable agreement with experimental spectra for the UV visible spectrum, which is shown here. And here you have cuts in the potential that shows that it's really essential to include the phi equals 0 distortion to describe correctly the conical intersection between S0 and S1. So before I show the full dynamics, I want to show what is happening when a wave packet that is created on the S1 state is going through the NAC region. So in the simulation, you have on this frame the dynamics of the population. This is S1, and here you have the coherence, electronic coherence between S1 and S0. And you see that as long as the wave packet overlap, we have a nice coherence. So this is the revival of the coherence that was discussed this morning. S1 comes back in the NAC region, and again, the wave packet creates the coherence, and you see here again the coherence appearing. So the revival of the coherence in this situation are just governed by the motion on the S1 state and how long it takes to revisit the region of the conical intersection. So we understood from these studies, this simulation around the conical intersection, that the place where the wave packet is on S1 is going through the conical intersection in phase space is very important to determine the yield in quadricyclane versus the yield of going back to the norbornadiene. So we try different positions around the conical intersection to try to understand what is the most optimal situation. And this is also a complicated picture, but we saw that the position 4 and 5 were kind of very interesting because 4 correspond to an early transfer to the quadricyclane form, and 5 you see that the transfer takes much longer. And so we took these two positions, 4 and 5, and we back integrated to the Frank-Condon region, and then we understood that if we polarize the UV pulse that excite the system along Z, we will reach the conical intersection through the position 4 and have an early transfer to the quadricyclane form, while if we start with a UVX excitation, we essentially excite sigma 1 in the Frank-Condon region, and we will get dynamics that looks like this violet one. So while I forgot to say, for the UVZ pulse, the interesting point is that we are selectively exciting S2 in the Frank-Condon region. S3 is a dark state, but there is a strong non-adiabatic coupling between S2 and S3 already in the Frank-Condon region, and then we have an electronic coherence that travels to the position. So we studied in details these two dynamics because one is a traditional femtosecond dynamics that excites selectively a given state, the S1 state, while here we built with the excitation an electronic coherence between S2 and S3 that through non-adiabatic coupling then transfer to S1 and then transfer to S0 and to the quadricyclane form. So we have these two paths, and here we control the two paths by the polarization of the exciting short femtosecond UV pulse. This is to show what happens during this dynamics. So here we have, we are starting, we go in phase space through a path that is essentially on S1 with UVX. We have an electronic coherence that finally reaches S1 from an interesting position with the UVZ excitation. This is the population in product and in reactant if we start the dynamics at these two positions. So you see that, as I showed before, we early populate the quadricyclane with the UVZ pulse, and it's a much later rise in the quadricyclane with the UVX one. This is here the population in the different region of phase space, product and reactant on S0, and the total in the product, which is much higher than the product on S0 because we have a lot of population in the excited state on the side of the quadricyclane product. This is what we obtained for UVX. This is what we obtained for the UVZ excitation. Note here that the Y value here is much larger for UVZ. And so it translates by the fact that at early times, if we look at the yield in product that is in quadricyclane, the normalized yields, we have a much higher value for the UVZ pulse than for the UVX pulse. These are the snapshots of the coherence here. There is not much action as you can expect for the UVX excitation because it's essentially what I showed you in the movie. Each time S1 is getting at the conical intersection, you are creating an electronic coherence. And if S1 goes back to the Frank-Condon region, you also have a revival of the coherence in the Frank-Condon region. For S2, S3, in the S2, S3 coherence, you see that it is traveling in this three-dimensional space, transferring from S2 to S1, and then from S1 to S0, and you then transfer to the quadricyclane product. What we next did is to try to understand how this coherent dynamics affect the amount of electronic density that would be localized as a function of the dynamics in the old bonds that is defined by the red volume here, and in the new bonds that is defined here by the blue volume. So it means that at every grid point we define this volume because at every grid point we have a different geometry, and then we compute the amount of electronic density either in the red cylinders or in the blue cylinders, and it is beating in time because we have a coherence, and so we can separate this electronic density in the bonds into a population term and into a coherence term. You see that in the case of the UVZ, we do not have much action because we do not have a long time coherence. It revives at 50, 100 and later, but we never have very prominent coherent terms, while in the UVZ, because we create this S2, S3 electronic coherence, we see it much more prominently. When we look at the population, you also see that what we see for the UVX is the electronic density going out of the old bond and building in the new bonds. Then each time we go back through the conical intersection, you have exchange of population between the old bond and the new bonds. And at the end, we have some equilibration, as you would expect if globally we go to quadricyclane. So the point is here that the electronic dynamics in the bonds essentially reflect the determinantal change in S1 as the wave packet is traveling. While for the UVZ, where we have an electronic coherence, we see a very fast, much faster beating between the old bond and the new bonds that are really due to the fact that we have beating and population exchange between the S2 and the S3 state as the wave packet is going to the quadricyclane region. So you have a cartoon here of the amount of electronic density, or actually the difference in electronic density from a point where we have a maximum in the new bond and a point here that have a maximum in the old bond. So we have an excess of density that is building in the new bonds between these two times. And of course, when you go to the next oscillation, you see the opposite phenomena. The density is going back in gray to the old bonds, and we have less densities excess in the new bonds. So the next point that we wanted to try to understand is if we can probe this motion of the electronic density, that we can relate to the motion of the electronic density between the old bond and the new bonds. And so we looked at the time-dependent dipole, since it has a term here that reflects the electronic coherence. We looked at the different components of the dipole, how they developed as a function of time. And because we want in the end to go to spectroscopy, we took also the emission dipole, the Fourier transform of the time-dependent dipole. The interesting point is that we see that when we go for the UVX excitation through the conical intersection, we see that it's the Z component of the dipole that is developing. And so it means that we will have low frequencies in the Fourier transform that will be a signature of the passage of the wave packet through the S0, S1 conical intersection, while for the UVZ, the one that has a coherence between S2 and S3, we see very nicely that a dipole along Y develops, and this dipole is really reflecting the presence of the S2, S3 coherence in the wave packet, and will also translate in low frequencies below, much below 1 eV when you take the Fourier transform. So we are suggesting to probe this motion of the electronic density using transient absorption spectrum, but we computed not ATAs from core excitation, excitation of core orbitals. We suggest as a probe to use a short IR pulse. So we computed this response function using the formalism developed by Ken Schaefer and his group. The results are shown here. This is the result of probing the UVX dynamics, so the dynamics that essentially takes place on the S1 excited electronic state. This is probing the UVZ dynamics that involves coherence. Yeah, I am essentially done. I have how many? 2-3 minutes?
2 minutes.
2 minutes.
3 minutes is fine.
Okay, so we see here we were able to show using an IR pulse that is polarized along Z to catch here the half period of the S1 state as it is going through the conical intersection. Here we have actually a period of an electronic coherence that is S1 and S4. And in the case of the S2, S3, we see the nice 20 femtosecond beating that corresponds to the S2, S3 coherence. I will not have much time to explain our recent work in the cation of CH4+. But Caio, who is attending the meeting, has a poster on this work. Here we are interested in the ultra-fast dynamics in the 3 lowest excited state of the methane cation following sudden ionization by UV expulse, and inspired by an early paper of John Marangos on a science paper on 2006, what are the structural changes that occurs as the wave packet is created in the Franck-Condon region, go back to the ground state of the cation and visit the different minima on the ground state of the cation, which can be D2D or C2V. So here it's a 2-dimensional simulation. The important point is to describe correctly the initial state. So we are using the sudden photoionization approximation, and I think my time is off. So I leave you with the conclusion. I think that can be summarized by the fact that electronic coherence are very important and can be used to control the dynamics, and that one can also use short pulses and non-equilibrium density to steer the nuclei towards the product, adjusting parameters like the carrier envelope phase, the excitation wavelengths, and the polarization of the pulse. Thank you very much.
Thank you very much, Françoise, for your extremely interesting talk. So now the floor is open for a few questions. So at the moment, I don't see any question because it takes a little bit of time to write them, of course, not to express them. But I can actually start a little bit saying that I was impressed indeed in this ability to actually let the nuclear dynamic and the electron dynamic to talk together and actually interact. So you were saying that indeed the electronic coherence can actually steer the nuclear motion. Could it be also possible the other way around, that nuclear dynamics can actually influence then the electronic dynamics in the end?
Yes, I think it's an interplay between the two, and this is what I was trying to show. In the non-Bernardine, this interplay is very clear, because when we excite a single electronic state, there is no electronic coherence as soon as S1 is going out of the Franck-Condon region. There you have one with the ground state, and then it's really the nuclear motion that builds the electronic coherence. And so the point is really to exploit the interplay between the electronic coherence that is built by the pulse and how it is modulated by the non-adiabatic couplings that is changing the phase relation between the different components of the wave packet.
This is actually beautiful. And okay, I don't see still a question. Let me check if I have something else. I know, we have a question from Danilo Matzel-Yuk, sorry my pronunciation. So it's asking, you mentioned you use 2 dimensions to describe methane. What were these dimensions and how did you choose them?
Okay, can I go back to my slide?
I think you can share again your screen.
I can share again my screen. I was very quick on this point. Thank you for the question. No, wait, I need to stop. I did, sorry. Where is it? Oof.
Maybe exit the presentation mode and leave it.
Yeah, I exited the presentation by mistake, but here it is, right?
Yeah.
So we decided to take a linear combination of Cartesian displacement, and I show here how they have, what are the weight actually, right, over the normal mode of the TD form. And so you see that we have a coordinate that essentially allows us to go in the direction of the C2V minimum of the ground state. And so it has weights that are distributed on the 2 lowest E mode and the T2 mode and the second T2 mode and the third T2 mode. And for D2D, we did the same. And there we have coordinates that essentially correspond to the E mode, the first E mode of the TD geometry. How we actually choose them it was to take a vector that goes from the TD geometry to the D2D minimum or to the C2V minimum, and we added a small distortion here that has to describe the distortion of the non-adiabatic coupling in the Jahn-Teller region. It's the same idea as what we did with Norbornadiene. Of course, to choose coordinates is always a very arbitrary procedure, right? It is especially when we have to reduce dimensionality so drastically.
Okay, thank you. There is still space for the last question from Fernando Martin. So he's asking, do you expect that the sum of the coherences you observe in the TIS survive when you average over molecular orientation?
This is a good question. I think that some of them will survive, but we need to check this point. Right here, it is true. We consider the molecule that is oriented, and so that and we can orient Norbornadiene because the ground state has a dipole, permanent dipole that is strong enough that one could hope to orient it. I think it will be easier for us to check the effect of random orientation in the meta and cation work, and this is what we started to do. And there I can say that our preliminary results show that the sum of the coherence do survive random orientation with respect to the direction of polarization of the field.
Okay,
but this needs to be checked for sure.
For timing reason, I cannot allow any other question. Well, there are no other questions anyway. So thank you again, Francoise. And now we go on with the next speaker, which is Janaky, who will present ultrafast dynamics in
Laura was unmuted. Welcome, everybody. I hope you can hear me well and see my screen well. As it was said, my name is Janaky. I'm from Szeged, Hungary, and I'm representing the Eli Alps Research Institute here. Sorry, so now you can also see me. And I was asked by our scientific director, Katalin Varjú, to present on some of the more application-oriented aspects of the research activity which is going on within Eli Alps. And I see that this is quite different from the talks which were delivered yesterday and today, but I hope I can show you some insights how ultrafast science can be employed in materials chemistry. Specifically, in this talk, I'm going to focus on charge carrier dynamics in semiconductors under electrochemical control, because this is an emerging field, as ultrafast dynamics has been around for a long time to study semiconductors, but quite recently it was discovered or found that those studies have little or limited relevance to practical devices because these materials behave very differently under charging conditions, which is indeed the case in many applications of semiconductors. So our idea was to develop an end station within Eli Alps, which is available for the user community, where we can have electrochemical control on these semiconductors while we study light matter interactions in these materials. So most of the work which I'm going to present now was carried out in collaboration with different partners around the world. And we are implementing these devices in Eli Alps. And in the second part of my presentations, I will show the first results which were actually measured in Szeged at Eli. But the results in the first part of my presentations were gathered together with my group at the University of Szeged, with Professor Prashant Kamat, the University of Notre Dame, and the research group of Teanu Pulleritz in Lund. So why do we want to study semiconductor interfaces? So we are interested in solar energy conversion at different irradiated semiconductor interfaces. If we talk about solid-solid interfaces, then we focus on photovoltaic cells for electricity generation. And if we talk about solid-liquid interfaces, then we are talking about performing chemistry with these photo-generated carriers to generate valuable materials, so-called solar fuels or solar chemicals. And I've just highlighted two things here. One is the recent boom in perovskite photovoltaics. So it was discovered something like 7 or 8 years ago that a special group of materials, which I'm going to introduce later, so-called lead halide or metal halide perovskites, are very attractive in solar energy conversion. And we have seen a very rapid increase in the power conversion efficiencies over the past 10 years, which is now over 25%, rivaling the best silicon solar cells. And similarly, the research effort has been tremendous. So we can see that thousands of publications are being published nowadays on this field, which is published by hundreds of thousands of other papers. Also, recently, there is more interest or increasing interest in solar fuel generation because we would like to store the energy of sunlight in chemical bonds to overcome the intermittent nature of renewable electricity so that it can be stored. One example is when we can perform water splitting, so for example, hydrogen evolution and oxygen evolution on semiconductor electrolyte interfaces, but to fabricate efficient and stable devices in both scenarios, we really need to understand the elementary processes at the interfaces. Whether we are talking about a solid-solid interface, let's say a perovskite interfacing an electron transport layer and a hole transporting layer, or semiconductor electrolyte interfaces. And to understand the elementary processes, we need ultra-fast methods under operational conditions. Actually, 3 years ago, when Eli Alps was still in the implementation phase, very much at the beginning of the implementation phase, so the first lasers were just being implemented, we organized a conference in Szeged and invited some of the key peoples in semiconductor electrochemistry and photoelectrochemistry, and had a very nice brainstorming on what is needed for the field, how we can get further to even better systems, better devices. And there were two key conclusions. Actually, one was that we have to take into account three factors when we study a solar energy conversion system. So the time scale of the process, the size or spatial dimension of a given phenomena, and the electronic complexity of the material what we are studying. And it turned out that one of the key challenges in solar energy conversion systems is that it spans through several orders of magnitude in time scale, several orders of magnitude in size, and it can have a very different electronic complexity. So we need to cover a very broad range. It also came up that we need operando or in situ tools to get better understanding of these elementary steps which I mentioned, because under operating conditions, under illumination, under irradiation. We have charging, discharging, and other phenomena which can indeed affect the performance of the materials. And XC2 measurements in air or in vacuum of these semiconductor materials or even devices doesn't really give similar or useful information. And here comes the mission of Eli Alps, which I don't want to talk a lot about because you might have seen this slide before. But Eli really wants to be the user facility where we can study different systems and different phenomena which occurs at the ultra-fast time scale, but also with high spatial resolution. So we are really focusing on this. And actually, as I've shown on the previous slide, this is exactly the range where what we need for better understanding solar energy conversion devices. So a few words about these wonder materials, these perovskites, which I will be talking about in my presentation. So generally, it's a crystal structure named after a Russian mineralogist. So any material which has this kind of structure is considered to be as a perovskite. Specifically, when we are talking about solar energy conversion, we focus on two different groups: these hybrid organic inorganic perovskites, where we have an organic cation, lead or tin metal, and the halide coordinating to these, or we also have all inorganic perovskites. This is the crystal structure. So as I said, we already have very high energy conversion efficiency and other optoelectronic applications. What are the key factors which allow these applications? So it has a very large absorption coefficient, which means that it's enough to have 1,000 times thinner films than in case of silicon solar cells, which obviously makes a very good argument in terms of cost and producibility. Depending on how we play with these composition, we can tune the band gap in a relatively broad range, which also allows to make tandem systems with different band gap values so that the solar spectrum can be very nicely covered. It has very small exciton binding energy, excellent charge carrier transport property, very tolerant to defects in the crystal structure. Because of this very long charge carrier lifetime, so we can extract a very large fraction of charge carriers. And as I said before, it's very simple to prepare them through solution chemistry. So these are very interesting materials. And so how we approached this method is that we used conventional pump probe type techniques. The novelty in this approach was that instead of just putting our semiconductor material in the focus of the light source, we used an electrochemical cell, and this is just a schematic, but instead of just having the semiconductor material here, we have a full electrochemical cell or solar cell or what semiconductor we would like to study, and we have an external potentiostat galvanostat source through which we can employ electrochemical bias and study the effect of this bias on the charge carrier dynamics. With in different systems, we study different features, either induced absorption or ground state bleach in most of the cases. So as I said, we started with collaborative efforts. Since that time, we had no system available at Eli Alps, which is not the case now. So now we have our own system. But first, I will talk a little bit about our precedent data. One where we have first described this phenomena for perovskites, and then also we extended it to p-type semiconductors, for example, copper iodide, and we have also revealed a mechanism on how hole injection affects the stability of these materials, and we also used transient absorption in this case to monitor these changes in the perovskite materials. So as a few examples, as I said, so we started with cesium lead bromide. It has a small exciton binding energy. After the pulse, we see this ground state bleach, which is then relaxing in time. And what we found is that this relaxation kinetics of this ground state bleach, so basically the recombination kinetics of these photogenerated carriers, depends on the applied potential in the system. So going from a negative bias to a positive bias, which we see a change in the decay kinetics. So we wanted to be more quantitative to uncover what is behind this phenomena, and we carried out first experiments where we only had the cesium lead bromide semiconductor on a conductive glass, and in that case we have seen no effect of this polarization in the lifetime, which was extracted by fitting these kind of kinetics. This is a case when we have an underlying TiO2 film of cesium lead bromide, which is indeed the case in all solar cells, where you have a electron transport layer which captures the photogenerated electrons from cesium lead bromide and transports it to the external circuit. In that case, we have seen a reversible dependence on this polarization. So indeed there was an effect, and we were interested what is behind it. And actually we came up with an explanation which was after supported with many further experiments, but very briefly. So when we have a negatively polarized electrode, so all the TiO2 particles which are beneath the cesium lead bromide are charged, negatively charged because of the negative bias polarization, then there is no pathway for the electrons to go from the cesium lead bromide to the TiO2, while if it's positively polarized, then there is an accelerated transport of these electrons, which indeed results in a faster kinetics. This is actually very important because it explains a lot of artifacts which are reported in the literature. Many people shine light on their solar cells for half an hour or 1 hour before they start actually the characterization measurements. And we have shown that if you shine light, you can charge your underlying TiO2 layer, which is a transient phenomena. So if you run your solar cell afterwards, then it will disappear within some time. But stationary as a transient phenomena, you can show better performance just by this light soaking, and we were able to explain the mechanism of this trick, which is unfortunately quite often employed in the literature. So we went further in collaboration with the University of Lund. So once we have seen that the TiO2 has a very pronounced effect on this charge carrier dynamics, we wanted to check what is the exact role of this electron transport layer, what is how the properties of this electron transport layer affect the charge carrier transport. And this is an ongoing project. We started with single crystals of rutile phase of TiO2, and we use the mesoporous TiO2 as comparison because that's the most generally employed TiO2 layer. And what we have found that the electron transfer from cesium lead bromide to TiO2 is very much affected by the underlying TiO2 layer. And again, this is preliminary data, but what we have seen is that in the case of we have a much faster kinetics compared to the other two cases, which is mainly a surface area question and the defect richness question. And we are elaborating on this right now with also other TiO2 samples. We extended this method to a p-type semiconductor, so copper iodide, and we have seen a similar effect on this ground state bleach based on the applied potential. Just there is an opposite effect because now we are talking about whole transfer from copper iodide to the underlying electrode substrate. So with more positive bias, we have the longer lifetime. And what was interesting in this case that again the system was very sensitive to the history of the electrode surface. So if we charged or discharged the electrode even after a certain time, it remembered on the history. So the lifetime was changing simply with the time, which was again a worrying observation for solar cell studies. One more example from the past. We have studied the effect of electrochemical hole injection into mixed methylammonium lead bromide iodide systems, and we were able to show that this hole injection and hole trapping is the first step which induces corrosion in these materials, and this was very useful for understanding instability of these mixed halide solar cells. And transient absorption again helped us to see how this corrosion process progresses, because we gradually dissolved the iodide domains from these mixed halide perovskites and got the metal ammonium lead bromide material, and the transient absorption features were very similar to the control sample, which was methyl lead bromide. But so this was the past, and we were always thinking that it would be fantastic if we cannot only track the decay of these transient signals, transient absorption signals, but we could also follow what happens before that decay starts. So far we were not able to tell anything about the phase of hot electrons or hot holes. We have not known anything about carrier thermalization, carrier cooling, and that's where the lasers of Eli Alps came into play. And this is the area what we are exploring right now. So we have designed a new electrochemical cell, which is gas tight, purgeable. We can also heat it or cool it if necessary. And we have validated our setup, which uses this electrochemical cell. It can be used together with two different lasers within Eli Alps, either the HR laser or the Silos laser. All the experiments which I will show from now on were carried out with this HR laser, which is a 100 kilohertz laser. So we have a very good quality spectra within very short time frame. This is our setup basically, which is a combined setup not only for transient absorption, but we also have terahertz generating part in the setup, so we can carry out terahertz probing of the charge carriers, which I will mention later on why that is interesting. So this is how it looks like. We have a sample holder for not only for electrochemical samples, but if someone is interested to study, let's say, suspensions or solutions of quantum dots, for example, then that is also possible. We have an air-free and moisture-free atmosphere. We can purge it. The whole box is actually sealable, and this is where we carry out our measurements right now. So just one example, very preliminary. This is from last month, so it's really new. These were on cesium, lead, bromide, iodide mixed materials, similar decay kinetics to what we have seen at our collaborators in Lund and in Notre Dame. But what is interesting here is that we can also track the initial phase of these processes, how it builds up. In this case, this is on a few hundred femtoseconds time scale, how that ground state bleach develops. Now we are still working on the spectrometers and fine tuning them, but actually it's very promising that already we can track these processes with our system. And now I would like to show a few examples what we would like to study with even faster laser sources in Eli Alps. And these are not our own data, but these are what inspired us to develop the setup in this direction. So for example, lead iodide, but all these metal halide perovskites have a fingerprint region in the XUV energy range. So this is characteristic for the both the hole and the electronic structure of these materials, and any change induced by electrical charging or discharging can be monitored in this wavelength range, which is actually indeed the wavelength range for some of our ultra-fast sources. Furthermore, if we think about the workhorse perovskite methylammonium lead iodide, we can also distinguish between different carriers based on what kind of light source we use for our transient absorption measurement. So the idea is basically to be able to perform all these measurements with the same setup, just channeling in different light sources into our spectrometer. And as I've mentioned in the case of my one of the previous slides, we are also performing spectroelectrochemical experiments with terahertz probe. For this, we had to design a very special electrochemical cell to avoid.
You have 2 minutes.
Yeah, perfect. To avoid the absorption of the terahertz irradiation by our solution. So we only have a very thin film. This was actually inspired by the group at Yale. We developed it a little bit further, and why this is important is that it can distinguish between the different charge carriers, which is extremely important for us. We can combine this with electrochemistry by introducing charge carriers to different trap states of these materials, and we can actually validate the concept, the role of different charge carriers in the conduction mechanism of different semiconductor materials. Just one example, this is also not ours, how terahertz absorption can be correlated with photoluminescence. And one final thing, what I would like to show, and which is our ultimate goal, as I said, to be able to perform both spatially and temporally resolved experiments. And this is our hope also within ELI to develop this multispectral imaging end station, where we can distinguish between different domains of semiconductors. So for example, in this case, this is a two-dimensional polysulfide semiconductor, which has bulk parts, few layer domains, and monolayer domains, and really check how this layer thickness or how these structural features affect charge carrier dynamics. This is our data. This one on the right hand side is from the literature, but we are aiming to do similar things. In this case, they have shown how the terahertz signal, terahertz absorption signal changes in the case of a single layer and tri-layer sample of polysulfide, and how it changed with the excitation energy. But indeed, you can see that there is room for experiment, also spatially resolved experiments. And I guess my time is over. So with this, I would like to thank you for your kind attention.
Thank you so much, actually, Xavier, for the very interesting talk and many options offered to actually study electrochemical aspects of these devices. And so in my past, I actually did a little bit of electrochemistry, and it was nice to hear.
Okay. Yeah, I know that this was very different from the previous talks, but what I just wanted to highlight actually that there's a lot of room. So there are of course technical challenges. For example, as I said in the case of terahertz, that you cannot use regular electrochemical cells because all your terahertz irradiation will be absorbed
Exactly.
by your solution.
That was my question actually. So how do you intend to actually perform terahertz measurements in basically a liquid system?
Yeah. So how we do it is that we have a special cell which only have 60 micron thick space where you can feel the solution, and the electrodes what we use and the windows are all patterned, so they are transparent from that perspective. So these are technical challenges, but once they are overcome, then all these methods are very powerful.
Very interesting. So at the moment there are no further questions, so I take a little bit of time. So I encourage. Oh no, we have. Yes, indeed. Still from Fernando Martin, I have a question. So very interesting talk. Do you expect to reach sub-femtosecond time resolution with the new experimental setup you mentioned at the end of your talk? Would you maybe access electron dynamics?
Yeah, well, that's the ultimate goal of what we are doing. In principle, I don't see any reason why not. The thing is, in Eli Alps, the main goal is to first have all our sub-femtosecond lasers running in a very reliable manner, and start with gas phase processing, and all condensed matter studies comes after. So basically, what we would like to do is to have a very reliable end station by the time when we will have all the access to the sub-femtosecond lasers. But yes, so we would like to see electron dynamics ultimately.
Very interesting. So looking forward. And for the interest of time, I think I cannot allow for any other questions, so we keep on time. I would like to thank again Xavier Janaky for the talk. And I would move to the next speaker, Amini, who will present laser-induced electron diffraction molecular imaging.
Thank you very much. I would like to first thank the organizers for the opportunity to give a presentation today. So I will also come from a slightly different perspective as well. I will mainly focus on, well, giving a perspective on time-resolved elastic electron scattering in determining molecular structure, and also in the use of time-resolved nuclear dynamical measurements. So here we have a static X-ray diffraction image of crystallized DNA, and it's showing a double helix structure as given by this cross feature. And my goal as a scientist is to capture time-resolved snapshots of the molecular world, whether that be it in the rotational and vibrational motion of molecules on the picosecond and femtosecond timescale, or in tracking electronic motion on the attosecond timescale. And the ultimate goal, my ultimate goal, is to not only measure the nuclear dynamics on the tens and hundreds of femtosecond timescale, but also to focus on the very first few femtoseconds of the chemical reaction, and to try to measure some kind of electronic dynamics simultaneously as to nuclear dynamics. So to directly image ultra-fast dynamics in isolated molecules, we need sub-angstrom spatial and few femtosecond temporal resolution to track atomic motion. And this can be typically achieved using diffraction imaging techniques that employ either electrons or photons as scatterers. In my talk, I'll mainly focus on electron diffraction because electrons have a scattering cross-section that is typically 5 orders of magnitude higher than X-rays. And in addition, electrons have a smaller de Broglie wavelength than X-rays. So how is elastic electron scattering used in structural retrieval? Well, here you have basically an incoming planar wave of electrons that can scatter against your target sample. So in this case, a diatomic. And what can then happen is the incoming electron can scatter with a certain scattering momentum and a certain scattering angle, where a momentum transfer has occurred between the electron and the target. And the momentum transfer is simply the difference between the momentum vector before and after scattering. And in the end, we detect this scattered electron on a detector through a specific solid angle element. And this detected interference signal comprises of two contributions. Firstly, it consists of a atomic sum of incoherence signal, which is where we have a planar wave that scatters onto a single atom. And this basically doesn't encode any structural information. And more importantly, the second contribution is from the molecular interference signal. And this is where our incoming plane waves scatter onto two atomic centers. And importantly, the resulting scattering waves can interfere. And this encodes structural information because it's highly dependent on the internuclear distance. So in a measurement, typically you can measure the total molecular, or you can detect the total interference signal. And here you can see that the molecular interference signal gives you a sinusoidal contribution, as you can see here. And this polynomial background signal is basically our atomic sum of scatterings, basically. If we Fourier transform our total electron signal here, we can then obtain the internuclear distances between the different atoms in our target sample through this radial distribution. So let's focus on ultrafast electron diffraction. Ultrafast electron diffraction is a field-free version of electron diffraction. How does it work? Well, basically you have a ultraviolet light pulse source that impacts onto a photocathode, typically made of copper. And this then generates pulsed electrons that are accelerated to kilo electron volt or mega electron volt kinetic energies. And ultimately, the pulsed electron beam can be focused both temporally and spatially onto the target using radio frequency fields and magnetic fields. And the resulting diffraction pattern is then measured on a detector. So this provides a bright source in single shot mode with up to 1 million electrons per pulse. But because of this, because of the number of electrons in the pulse, you have a severe space charge issue in single shot mode. And that means that due to Coulomb repulsion between these many electrons, the pulse duration of the electron bunch is limited to hundreds of femtoseconds. If we accelerate the electrons to kilo electron volts kinetic energy regimes, which is possible in a tabletop source setup, one can achieve down to 350 femtosecond pulse durations. Otherwise, one can use a linear accelerator to accelerate the electron energies up to mega electron volt. And recently, colleagues have achieved up to 150 femtoseconds pulse duration. So one clear motivation then is to try to achieve shorter time duration of electrons, and the simplest way is to go to the use of a single electron. So here I'll show you the use of a laser-induced electron diffraction. What we have here is basically a s orbital of hydrogen atom. The dashed lines indicate the ionization threshold above which an electron can be released. As the s orbital has reached a certain point in the electric field above the ionization threshold, an electron is released. It is then accelerated, and then it is returned, and in this case, elastically rescattered. And we actually detect and measure this elastically scattered electron. It's analogous to the process of high harmonic generation in the sense that the third step is different. You have recombination to make attosecond pulses of light. In this case, we care about the elastically scattered electrons. So let's look at a quantum mechanical view of this same process. Here we have a p orbital argon, p orbital in an argon atom, field free. As it enters the peak of the pulse, we release an electron wave packet, and then we accelerate and drive back the electron wave packet onto the argon atom. And here you can clearly see the constructive and destructive interference of the returning wave packet with the target atom. And this wave packet has a de Broglie wavelength and a certain wave packet spread x. So ultimately, one can tune these two properties depending on the wavelength of your driver laser, and typically we operate under the 3 micron mid-infrared regime. Why? Because we can then achieve sub-angstrom de Broglie wavelength, and our wave packet extent is also more than 100 angstroms. So a quick comparison then between LEAD and UED. UED typically operates in the forward scattered regime in terms of the scattering angle. And so you are a little bit limited to the amount of scattering information that you have, but it's still possible to extract structural information with a large momentum transfer window, which is important in the Fourier transform process. Whilst in LEAD, because we're covering much lower kinetic energies, the imaging electron has much more time to interact with the actual target. So what we have is a sensitivity not only in terms of kinetic energy, just like in UED, but also across the scattering angle regime, much further away from forward scattering. We can go to side scattering and even to back scattering. So we basically can extract doubly differential cross sections of our target. And a final comparison, although you can extract meaningful data on carbon and hydrogen in UED, when you go towards the side scattered and back scattered regimes, LEAD has orders of magnitude higher scattering amplitude for both carbon and hydrogen in this case than compared to UED techniques using, say, 20 kilo electron volts. So the advantages here for LEAD are that there is no space charge issue. We have a single electron that we image with. We can achieve sub-cycle timing, few femtosecond to attosecond regime, attosecond resolution. And LEAD is a coherent electron scattering source because the electron current generated from LEAD is around about 4 orders of magnitude higher than UED. Of course, one can argue that UED can achieve and close this gap by having a brighter source and more electrons, and this is possible. LEAD extracts field-free differential cross-sections from a field-dressed measurements. We are more prone, more sensitive to the detection of hydrogen atoms, which I'll show later on. And we can extract doubly differential cross-sections at a wide range of rescattering momenta and angles. And I want to also say some advantages that UED provides. UED provides a field-free probe of structure without ionizing or exciting the target, which of course happens in the laser-based approaches. UED is not prone to fragmentation of the molecule prior to imaging, and field-free beams from the technique of UED can be manipulated using magnetic fields to basically perform different types of electron microscopies. So what tools are then needed to perform LEAD imaging? Well, you need an enabling light source to basically be able to image your target sample. We typically operate in the mid-infrared regime of 3.2 microns using our mid-infrared OPCPA setup. So we operate at 160 kilohertz, and the reason for that is because of the wavelength scaling of the scattering probability. So the scattering cross-section, scales by the wavelength to the power of -4. So that means we need to have a much higher repetition rate at mid-infrared wavelengths than at near-infrared wavelengths. We operate up to a high 20 watt average power with typical pulse durations of 5 to 10 optical cycles. And in addition, we need a detection system. So we use a reaction microscope. I'm not going to go into detail, but briefly, we have a molecular jet of molecules that interact with a laser pulse. We then simultaneously detect electrons and ions on separate detectors using electrostatic and magnetic fields. And this allows us to detect the 3D momentum distribution of each of these particles, both together in coincidence, which is very important, as I'll show you in the next slide. So why is coincidence imaging so important? It's because in a strong field measurement, you typically generate lots of different fragments, lots of different background signals as well. So what you really want to do is to isolate your electron that rescattered against your target ion. So in this case, I'm showing you lead measurements on water. We want to isolate that. So we can do that through coincidence. Here is the electron 3D momentum distribution from all ions. And doing this electron ion coincidence, where we only look at electrons generated from the water plus molecular ion, and taking into account that we have cylindrical symmetry in our system, we can then look into our 2D momentum map. And if we basically integrate at, an arc area at different rescattering momenta, we can then build up a differential cross-section for this process. So here you see the electron counts as a function of rescattering energy. And in this particular region here between 0 and 2 UP, ponderative energy, these are just basically our direct electrons. So these are electrons that have flown away and have not been returned back to the target ion. And from 2 to 10 UP, we have our rescattering plateau. So these are electrons that did rescatter with our target ion. And here you can see in blue all electrons, and in black molecular ion electrons, H2O plus electrons. And if we zoom into this, you can clearly see that the sinusoidal molecular interference signal in the black from the coincidence data is much more pronounced than in the all electron data. So focusing on this rescattering regime, we can then basically calculate something called the molecular contrast factor. That is simply taking our total detected interference signal, and then basically we subtract our background sum of incoherent scattering signal, which, remember, we can do so by either doing an empirical background fit, or we can calculate this using the independent atom model, just as in the UED method. So this then gives us our molecular interference signal, and then we contrast that against our atomic background. And so so our MCF gives us a sensitive fingerprint of the molecular structure. If we Fourier transform this, we obtain our radial distribution. And in the case of water, we have two clear Fourier peaks, which correspond to the OH and HH internuclear distance that is slightly straightened than the equilibrium value of water. So we also looked into the mid-infrared lead of the C2H2 singly charged ion, and we were able to retrieve the equilibrium value of this structure. And interestingly, we also looked into the dication acetylene channel. And here we saw that our retrieved structure corresponded to a CH bond length that was more than 100% than that of the equilibrium bond length. And so we found that through state-of-the-art quantum dynamical calculations, field dressing the C2H2 dication molecule leads to strongly dissociative potential energy surfaces. And one can simply think of this as the dication basically Coulomb exploding, and we capture a snapshot 7 to 9 femtoseconds after it has ionized the singly charged acetylene. We also looked into the lead of CS2, carbon disulfide, and we actually measured, interestingly, a very bent and very symmetrically stretched structure. And this is in comparison to the ground state of the neutral molecule, which is linear. And we accounted for this due to the fact that we strongly perturb the potential energy curves under the presence of a strong laser field. And this field dress molecule, we found slightly bends and stretches to split the degeneracy of the delta U state into two bent states, an A1, A2 and B1, B2 excited state. And this slight perturbation allowed for transition to the bent B1, B2 state to become dipole allowed. And so at the peak of the pulse where we perform our lead imaging, we were imaging a bent and symmetrically stretched structure. So clearly you can see that lead so far has been focusing on simple molecular structures. And so I will focus on the next 3 to 4 slides on challenges of lead and future outlook. And one of the challenges is the ability to deliver gas phase molecular beams of large molecules. So as an example, we performed our water measurement at the room temperature, and that has a vapor pressure of around about 20 millibar. So this we found was perfectly fine. It was enough signal to do a measurement using a bubbler setup, which is simply a vessel that has water liquid inside that is then basically introduced into the ultra high vacuum setup to generate a molecular beam. Now, the problem is that if you go to larger molecules, such as steel beam, the vapor pressure is much lower. It's around about 1 millibar. And so one typical approach is to increase the temperature and heat the system to around about 100 degrees Celsius to increase the vapor pressure. But even then, that's still not enough to do steel beam measurements. Another important point is that larger molecules, more complex molecules, 20 to 30 atoms or larger, have quite a relatively low ionization potential. For example, steel beam ionization potential is less than 8 electron volts. So that means it tends to fragment very easily in the presence of very intense pulses. So it really is like quite a connected problem in terms of delivering a dense enough gas and performing these measurements at low enough intensities in order to get some kind of structural information. So another issue is the fact that you need to perform these measurements of lead under high rep rate and average power laser sources. Why is that? Remember, in order to detect rescattered electrons with sufficient signal to noise, we require high rep rate. And so this has a knock-on effect in the fact that you need to generate optical pump pulses, say ultraviolet pump pulses, with a very high average power and minimizing losses when you're actually generating these pump pulses. These are just things to be aware of. I'm not saying that it doesn't work. It can work and it does work. It's just things people have to take into account when doing high rep rate, high average power, lead and strong field measurements. Another issue is also, and another advantage even that one can use is aligning the target structure. Here you basically have the retrieval of the target structure that has been 1D aligned and one that has been perfectly aligned. And you can clearly see that the different features of the different atoms become much more clearer with alignment. And so one final thing I want to discuss, or two final things, but one final thing in terms of the future outlook of lead is the generation of sub-femtosecond VUV pulses. And Francesca has already discussed earlier yesterday on the generation of the third harmonic of 266 nanometer light near a single femtosecond pulse duration in a gas in a cell. And I will give a perspective on other techniques as well. Particularly, for example, you can generate these short pulses of UV light using hollow core photonic crystal fibers, as well as hollow capillary fibers. And why is this important? It's because the ultimate goal, I guess, is to generate an attosecond picometer molecular movie using UV pump and lead probe measurements, for example.
Kasra, you
So
have 2 minutes.
Thank you very much. So here we have basically the ability to generate self-compressed UV to VUV pulses through optical soliton dynamics that combine non-linearity and dispersion through SPM and GPD. And ultimately what you can generate is, a multi-octave supercontinuum, but more importantly, this tunable VUV pulse that can be tuned, the central wavelength of which can be tuned to different wavelengths depending on the gas pressure, the input pulse, energy, and things like this. And ultimately, one can generate 1 to 10 microjoules UV pulses with down to 1 femtosecond UV pulses. So one very final thing I want to discuss is the fact that there was a recent paper, a UED paper, at SLAC with a SLAC MEV source that not only looked into the elastic scattering of molecules, which gives you nuclear information, but also the inelastic scattering of molecules, which in fact gives you electronic information. So they looked into the percentage difference of pump probe minus probe only signals, and there is up to 15% change in this. And they found that the elastically scattered signal gives you a lot of nuclear information and changes in how a certain molecule, such as this, changes its structure. And very importantly and very significantly, in the same measurement, they were able to interrogate this inelastically scattered electron beam that was generated, which gave the following electronic excited state information. So here they have the signal integrated in blue and a calculation that they did, which they showed corresponded to the S1 population after exciting from the S0 state. So in summary, there have been mainly static lead measurements performed, but there is a big opportunity for many different groups to perform 2-pulse time resolved lead, which has not been yet achieved, but it's certainly still possible. UV pump lead probe harnesses the potential for capturing attosecond or few femtosecond molecular movies with picometer resolution. So as I mentioned, there's been a lot of significant mega electron volt UED institute-based measurements. So contrastly, tabletop KeV UED still is limited to 350 femtoseconds. And the best that's been achieved is around about 28 femtoseconds with a single electron pulse. And recently, it's been demonstrated that one can generate a train of attosecond electron pulses using optical dispersion and material dispersion. And finally, basically single electron lead generates suboptical cycle pulse durations and interrogation of your sample. So ultimately, lead and UED are highly complementary. Both have challenges, but importantly, both have opportunities. So I would like to thank my supervisor, Professor Jens Bigert, my colleagues, Tobias, Aurelien, Genial, and Blanca. Blanca is giving a poster, so please check that out, and our collaborators. Our funding agencies, of course, particularly ERC and University of Warsaw, and I would like to thank you for your attention. Thank you.
Thank you so much for Kasra, for the fascinating talk. It was actually very nice. So I leave the floor for questions. So since they are not popping up immediately because it takes a little bit of time, I might start with a smaller specification because I actually most probably missed it, sorry. So the definition of these scattered electrons is basically based on the kinetic energy of those electrons, correct?
Yes, exactly. Okay. So you have basically a contribution from the vector potential of your laser field, which is significant in the mid-infrared regime, as well as the return energy. So that's the energy at the instance of scattering. And then basically the sum of these two energies is what you detect on your detector.
Exactly, okay. So since I'm familiar with the detector, but I'm not familiar with the technique, So I was actually wondering how you actually define your pre-scattering electron, and it was actually very nice to see that you could actually recall these ripples in order to
Exactly.
actually get information about the nuclear information.
So LEAD is very analogous to UED. I mean, it really shows that you can capture and extract the molecular interference signal if you go into the high energy regime. So a lot of people have performed in the very first days of LEAD, near infrared and 1.5, 2 micron measurements, which is good, but you don't have that momentum transfer range, which is related to your high energy regime. The higher in energy you can go and the larger the range, then the bigger the momentum transfer range is in order to capture these molecular interference signals from the scattering process.
Still questions, so I will continue myself.
Go for it, no problem.
I don't see a question. So, because you discussed up to now the samples that are in the gas phase. So I was actually wondering, so you already know. So moving towards, also because that's what I'm interested for my future, is moving towards liquid or very exotic phases. Would it be able, for instance, to capture intramolecular dynamics or intermolecular dynamics?
So that's a very interesting question. So right now, I'm not aware of anybody that has performed LEAD measurements on condensed matter, but it's an interesting topic. And that's something I may have forgotten to say at the end of my conclusions. There is a potential for this. And I think this is a little bit analogous to high harmonic generation from solids. I think. I mean, look, you still have the 3-step process, but the last step is not recombination, but rescattering. I've had a very brief look with my colleagues at ICFO on the theoretical side. Initially, we think it might be possible to do a certain measurement on solids, for example, but we still need to look into the feasibility more of this. I want to also mention that ultra-fast electron diffraction field-free beams, in my opinion, have a great potential also in condensed matter physics research, especially when you can do tabletop measurements. So if you can tackle this problem of the RF jitter, the microwave cavity jitter, which is used to compress your pulses, and the laser pulse, and in addition, the fact that you have space charge issues, if you can solve these 2 problems and reach the sub 100 femtosecond barrier, then you can do a lot of very nice electron diffraction time result research in gas, not only gas phase, solid phase, condensed phase matter.
Very interesting. So I have 2 questions from Valerie Blanchet. So the first one was, how do you evaluate the empirical background? And the second question is, do you need to be in coincidence counting rate to identify the backscattering electrons?
Excellent questions. So just to answer the first one, I'm sharing my screen again. I think you can probably see that, right? So I did say this very quickly. Apologies if I rush through that point, but basically you can see that we can fit a polynomial fit to our actual DCS that we measure experimentally. And this we can then extract as being our empirical background. Right, so we do a polynomial fit, say 3rd or 4th order, for example, and then we subtract this away from our total DCS to get our molecular interference signal. Now, something I also mentioned is another way to do empirical background subtraction is also to calculate what the scattering signal is from each atom using the independent atom model. And then you can take the incoherent sum of these. So this is also possible, and it's analogous to UED. Now, the second question, I remember, I think it was about...
Do you need to be in coincidence counting rate to identify the backscattering electron?
So from our experience, we found that it really matters on what type of molecule you look at, but generally I would highly recommend to perform coincidence measurements because, well, one thing about backscattered electrons is that they reach a very high energy regime or a very high scattering momentum. So already you can see that in your spectrum, but depending on the signal to noise and the scattering probability, this is heavily dependent on your molecule that you're looking at. So if you're looking at oxygen or something like this, okay, you can probably do so without coincidence, but it is much easier to do these lead measurements with coincidence imaging and with mid-infrared laser sources, which I advocate very strongly if you want to do lead measurements to get molecular structure information. This is separate to getting electronic structure information, because there you can do so if you look into the low energy elastically scattered electrons or inelastically scattered electrons.
Okay, thank you so much also for the interesting discussion. So now we have to move to the last speaker of today, Joachim Küpper, who will present strong field ionization and rescattering in the molecular frame. I leave the floor to Joachim.
Okay, thank you, Lara. I hope you can all hear me and see my slides. So I wanted to quickly
perfectly.
hide this menu. And I would also like to thank Katarina and Fernando and all the organizers for setting up this cool workshop, and all of you for sticking around for now and having actually interesting discussions and good talks so far. And maybe I should also thank Kasra for actually introducing a lot of what I want to talk about. And so that's really related to lead in chemical dynamics, but in the spirit of this being an attosecond or attosecond chemistry workshop or conference, I would really like to look at a little bit at both these processes. And maybe as a very generic, broad motivation really for all the work we do in my group, I thought I'd bring up this gimmick. And I mean, this is a very complex molecular machine, and I don't want to go to the details here because I don't have time, but essentially what we are getting at is, or what we would like to get is to really understand this machinery of life, biological, biochemical processes with essentially atomic physics rigor, and then maybe even eventually control it. And so the question is, can we actually use laser-induced electron diffraction for that? And how would that work? And how does that actually really fit together? And then I want to also discuss a little bit the electron dynamics underlying this. But in first instance, I should really thank my group who has done all this work, and all the funding agencies that allow us to do this work, to essentially have fun in the lab and in the office. And then I should point out there's really this group here on the left, that's a team, we call this the chemical dynamics team, that's performing all this work we're going to report on today. And the two other teams work actually really on experiments with biological macromolecules or nanoparticles and theoretical spectroscopy in a way of theoretical chemistry related work. And really mostly today I will report on work performed by Andrea Trapattoni and Jolaine Onfley, who were postdocs in my group, and by Evangelos Karamatskos, who was a PhD student and still is around a little bit as a postdoc for now. Okay, then I should exactly not forget to thank Arnaud Rousset from the Max Born Institute, who was involved in some of the experiments, and Umberto Di Giovanni from Uncle Rubius group, who did some very important TDDFT calculations using Octopus. So having said all this, we are really looking for new co-workers, and if you're interested, just come along and join us. Now, this is a model system for this biological system that I presented before, and also goes a lot back to actually the question that Laura asked just recently on condensed matter systems. And this is our simplest model for a solvated biological system. So this indole chromophore here is actually something that is UV absorbent proteins, and we attach water to it. And we would really like to understand how such a hydrogen bond is formed or broken. And the question is, how can we see this? And so one thing that I will briefly show later in the end is just to demonstrate this. So actually, if such a system in biology absorbs UV photon, then it goes into some electronically excited states. There's lots of electronic dynamics. And eventually, we believe now, when it's back in the ground state, for instance, this bond will actually break. And what you also see already, and this is very important in our experiments, that we actually literally do the experiment on a sample of molecules that are all exactly this reaction system and nothing else, out of this big zoo or soup or ocean of different molecules that typically exist in a gas phase. But so, I mean, what I sketch here, and this is really the result of a relatively moderate quantum chemistry calculation, that's kind of a model. But what we would see is reality. And so the question is, can we actually experimentally observe something like this? And this is what people have dubbed the molecular movie. But if you really want to understand it, what we have to see is the electrons. And so in the computer, that is relatively straightforward because we've calculated all the electrons before as well. So we include them in this picture. And what I show here is essentially an electron probability density distribution of all the electrons in the system. And if you now look at what happens when this bond breaks and forms, it's actually very little. Barely anything happens. And that's, of course, because we understand that such a chemical bond in the system, so this connection between these two atoms here, that's essentially 2 electrons. 2 electrons out of more than 100 electrons in this molecule. And so what you really have to do is we have to look at the individual orbitals that constitute this chemical bond. And this is something I really also to all of you looking at ultra-fast electron dynamics, I want to put out here as a challenge. And we have some ideas, but I'm not going to talk about this at all any further. But so what we then extracted here is actually a calculated wave function. And this is, in this very specific calculation, this, for instance, is HOMO minus 12. And in HOMO minus 12, you really see the signature of the chemical bond in the system and how this electron density arranges during the chemical reaction. And so in the long run, this is really what we want to see. So how do we do that? In our experiments, it's actually a little different from what Castra said before. And essentially prepare very cold supersonic beams, typically on the order of 1 Kelvin out of a valve. And then we even further control these with this electric deflector. This is essentially equivalent of a Stern-Gerlach deflector, which you can use to prepare, for instance, molecules all in a single conformational structural isomer, or in this one single aggregate of a molecule with the water attached, or even for small molecules, all molecules in a single quantum state. And then we fix these molecules in space. For instance, we 3-dimensionally orient them by electric fields using lasers and DC fields and smart combinations thereof. And then eventually, these are the samples that we image, in which we then have well-defined single molecular species fixed in space, and then we can directly image these molecules. And Castra already showed how this molecular frame measurement strongly increases information content, and that's especially crucial for these larger molecules. I should also mention that we typically, so in principle, the system runs at 1 kilohertz, but we typically operate it at 500 or 250 hertz, essentially because limited pumping speed in the vacuum systems. So just to give you an impression what one can do with this technology, I wanted to show you actually a real molecular movie. So this on the left is the probability density function of this O end of this linear OCS molecule in space, or really the 2D projection of that. And it's raw experimental data. This is directly read out from a camera. And the experiment that we did is that we produced a shaped kind of 2-pulse sequence of near-infrared laser pulses, which started a rotational wave packet. And then later on, we probed this with 2 micrometer strong field ionization. And what I really show you here is the momentum, or the momentum probability distribution of O+ ions from Coulomb explosion of these molecules. And obviously, I understand this is not attosecond, this is actually picosecond science, and so we have to increase the spatial extent, the temporal resolution here. But it demonstrates that it's actually feasible to directly image structural information in molecules with very high resolution and fidelity. And we can also easily understand this. I want to go through this quickly, but essentially, so the wave function of this linear rotor is a spherical harmonics. We start with all molecules in this J=0 state, and then if you impulsively laser excite this, essentially do impulsive Raman transitions to this M=0 states, actually also always with even J's. And So then you record this time-dependent probability density functions in a way. What we did here is we recorded the quantum carpet, so the complete periodic quantum probability density distribution of this molecule over time. And you can then disentangle that in terms of the rotational quantum number populations or the coefficients and the phases. And this actually turned out also, the reason we did this also was to improve the degree of alignment. This is kind of world record alignment. And what's important here is actually that we used the 2 pulses while you think to make a broader wave packet, and we did. But most importantly, to really control the phase, even at that level, the phase really determines in the end the performance of this experiment. So really saying, I mean, this is a way, A, we can very strongly fix molecules in space, and B, we can image even something as simple as Coulomb explosion imaging, the nuclear structure of molecules. Another thing I just wanted to bring forward is that really an old experiment we did together with Henrik Stapelfeld and actually Lars Madsen, who gave a very nice talk yesterday. I must say, I should really talk more to him, where we put a 3-dimensionally oriented molecule into a circular polarized strong laser field, in this case, to actually avoid recollision, to avoid rescattering, but to really look at the directly outgoing electron wave. And if you do this in these strongly controlled fixed in space molecules, I just want to point this out. What you see here is actually the photoelectron momentum distribution on this detector. And what you directly see here is actually that these electrons come out of a HOMO pi orbital. So we directly see the symmetry plane of the molecule that we can see. And demonstrating that you really can measure electronic structure in a strong field experiment. And I should point out, we are not the only ones. I mean, there are other electron imaging experiments by them, and there were also these high harmonic generation experiments that are referenced there at the bottom. And so putting this together, I already showed you that we can measure nuclear structure and that we can measure electronic structure. And the challenges are to do this with very high time resolution and also with very high spatial resolution. And especially regarding the spatial resolution, I now refer essentially back to the talk of Kasra just before me. And so we want to use this backscattering electron diffraction to really obtain to obtain atomic level spatial resolution in these kind of experiments. And I just really put this together as a slide I normally walk people through with quite some detail, but this is really the summary of a fraction of Kasra's talk. And it's really the explanation of laser-induced electron diffraction. I just want to point out that in principle, we really have this sub-cycle electron dynamics that we can use to look at ultra-fast processes. And I want to discuss that a little bit in the next slides. And I also want to point out that really doing this to the level of really measuring atomic, nuclear, and electronic probability density functions has still a number of open questions. And one of the really big challenges is to understand the tunneling process in the strong laser field from these complex molecules, which is typically still using atomic physics models. And so the question is, how can you really interpret this data for these complex molecules and use it to solve dynamic structures? Okay, just stepping back a little bit, and this is also something that was discussed in the question session then in the previous talk, is, so if you do a laser-induced electron diffraction experiment or a strong field ionization experiment in general, we can just use that half a laser cycle, that's a dashed red line, and then consider what energy electrons have when they rescatter on their own cation. And the point is really that there is a peak at about 3.2 UP, the polymotive energy, for rescattering energy if the electron was born at this 15 degree after the peak of the laser field time. And if these electrons are then backscattered, they actually end up at 10 UP final kinetic energy. And really, this is the only way to get back to 10 UP. And so that's really going back to your question, Laura. If you catch these 10 UP electrons in your photoelectron momentum distribution, then you know that it was born more or less at this 15 degree phase, and you know that it was rescattering at more or less 3.2 UP. And under these circumstances, you know the electron trajectory very well, whereas for other cases, it's maybe not so clear. For this, and we do an experiment to some extent conceptually very similar to what Kaspar presented, but also quite different in the sense that we actually use a velocity map imaging spectrometer. We pre-control our molecules, and we run this experiment at a nominal frequency of 1 kilohertz, or maybe half a kilohertz. For instance, in this experiment, we used then 3 millijoule of 2 micrometer pulses, which correspond to roughly 10 to 14 watts per square centimeter, and 50 electron volts per motive energy. And I should say that we really very carefully confirmed that under these conditions, we solely get single ionization of our molecules. So we don't see any double ionization events in the ion spectrum that we looked at. And so that's why we can spare the coincidence imaging. And then this is a photoelectron momentum distribution that you measure. On the left is a directly 2D projection of this measurement. And because we did this in an isotropic sample, in this case, we could then do an inverse Abel transform to get a 3-dimensional probability density distribution. That we can then analyze. The first thing, you can really plot the photoelectron spectrum from this, and you see this goes out all the way to 500 eV, or already, as I said before, I mean, so these electrons essentially rescattered roughly at 150 eV, the ones that we collect out here at the end. And so there we have already our sub-bond length resolution. And the way you analyze these spectra then is that you really, I mean, you look from the center of your image, you add the ponderomotive energy of the laser at ionization. Then around that, you can draw your Newton scattering sphere. And this is your like rescattering momentum vector. And along this line, or along this circle, you can extract then the differential cross section, very much exactly complementary to what you would get in the standard classical electron diffraction experiment for these kind of electron energies. And so here I plot the differential cross section extracted exactly around this ring, which corresponds to 120 picometer rescattering electron wavelengths. And I already plot 2 fits. And one thing, I mean, I already want to point out here, I will point this out another time, is so that we really looked at what do we actually rescatter off, and what very often people do is they take then the independent atom model and form factors for the neutral atoms in these molecules, because I mean that's what you can do easily. Whereas normally we know that we have a cation, but we don't know exactly where the charge is, or let's say most typically in molecules it's actually distributed over the molecule. But one thing that's often then realized is that the fit isn't very good at the smaller scattering angles. It's attributed to contributions of direct electrons along this line. But what you really see is that if you actually really simulate this for the cation, it becomes a lot better already. And so we switch from the differential cross section to the molecular contrast factor. Thank you, Kaspar, also for already introducing that. Here you see the same effect even more than, so you doing that, you see here in blue, that's a simulation, the same simulation I showed you before, now converted to contrast factor. We can derive bond lengths for this molecule, or really, if I put this together, what we derived is parameters for the CO length, for the CS length, and we also introduced a bending angle, which was then fit in this data analysis to 180 degrees, meaning to a linear molecule, because there was discussion out there in the literature that the molecule might bend under a strong field excitation, but that only happens at very much stronger fields. And here in white, you really see the result for the 2 bond lengths of our molecules with the error estimates. And in red, I plotted really the true experimentally known geometry of this molecule, which is kind of known from something like a microwave spectroscopy, what I would call the gold standard for static structures. And you see essentially we're dead on there. And so that's essentially confirming what others have promised and demonstrated before, that you can use laser-induced electron diffraction to measure very accurate structures, actually really now down to 5 picometers. And of course, we have potentially very high time resolution. I mean, this was just a static experiment. I confess that. We don't understand the time resolved experiments yet. That's why I don't show them. But you really see the very high resolution in the spatial extent. And but the point is, and Kaspar got at that a little bit, if you really want to go to more complex molecules like I showed you before, we have to do this in the molecular frame to obtain sufficient information on the real structure of such a molecule. And there are lots of calculations actually for X-ray diffraction in this old paper that really demonstrates this clearly. So we went to the molecular frame and we took the same OCS molecule and we did the same type of experiment. I actually show you in first instance now data obtained at 1300 nanometer, which is not really atomic resolution, but I show you that at atomic resolution, it looks, the story is really the same. We actually went to the somewhat shorter laser wavelengths for our theory friends, so they could actually do the calculations, which they couldn't do at the larger driving laser wavelengths. And so essentially what you realize here, and I have to go a little fast to that, seeing my time, sorry, but what you see here is that in the two, well, maybe I should go back. So we did this in two scenarios. So we once aligned the molecule parallel to the detector, and once we aligned the molecule perpendicular to the detector. So we have strongly aligned molecules, and then we measure the photoelectron angular distributions for the two cases, parallel and perpendicular. And then if you do this, what you actually see is that for parallel, the electrons have the highest energy electrons have a strongly reduced photoelectron momentum or photoelectron kinetic energy. And we see this in the experiment, and we see this in TDDFT calculations that Umberto Di Giovanni did, which exactly reproduced the experiment in that respect, in many other respects. But they still didn't really allow us to unravel what's going on, and therefore a graduate student of mine developed an extended, simple man, semi-classical trajectory type computer code to simulate these electron trajectories and this whole process, and it also shows the same behavior. And so essentially, we now have an experiment and two very different theories that say, okay, if you look into the molecular frame, it very strongly depends on how the molecules aligned with respect to ionizing laser, which is also parallel. So it's parallel to the molecular axis in this case and perpendicular to the molecular axis in this case. And that has strong influence apparently on this rescattering electron process. And the question is why this happens. And so these are the difference between these images. I skip over that. So using the semi-classical trajectory method, so that's really a molecular quantum Monte Carlo trajectory method with phases, we could essentially see how the rescattering process happens. So what we did is we then binned all these electron trajectories in terms of their relative ionization time. So, I mean, of course, we had a multi-cycle laser, so we had ionization and multiple cycles, but we then all shifted them on top of each other. And then we see the final momentum of these electrons as a function of the recollision phase in terms of the laser system. And what actually these shadows here at the 4s, at the 6, I should say, are some artifact of the calculations. But what you see here is essentially that, I mean, you get these 10 UP electrons exactly the way I described before. The electron flies away, comes back, scatters to 10 UP. But in the parallel case, if we do the simulations, we see that the signal is completely lost. And why the signal is completely lost is very much the same as in this benzonitrile experiment that I showed you in the beginning, where we saw the HOMO structure with this nodal plane. And this OCS molecule has a similar nodal plane, or it's a nodal line in this case. And so all the original electron emission is away from the laser polarization axis. And therefore, the molecule, the electron completely misses the molecule when it comes back. And then only due to Coulomb focusing near the cation, it returns closer to it and eventually we collide at the 3rd or 5th return. But that's actually something that was known before, that these later returns never go back to 10 UP. And that's exactly what we saw in experiment, that in this case, because we don't manage to go back on first return in the parallel case, we never get out to 10 UP. And this has good and bad things. The one thing is that you have to be very careful in the analysis of these laser-induced electron diffraction experiments, because they essentially always operate in this model here. Yeah, so you assume the electron goes away, returns, backscatters, and that's your classical backscattering electron diffraction experiment, which you can possibly describe by something close to a plane wave returning to your cation. But if you go to this parallel case in the molecular frame, the whole process works very differently, and the returning electron is clearly far away from a plane wave, and this is really what makes this analysis so complicated in these conditions. And that's really a complication, but at the same time, of course, you already see here that at least in principle, and we are still having to prove that, but you can now use just the orientation or the alignment of the molecule to have a temporal resolution on the order of the period of the laser, because here we get a lot of direct rescattering within the first laser period, but then if you rotate the molecule, that actually goes away, and we see rescattering at later times, which then really allows to do ultra-fast electron dynamics time-resolved measurements. I see that I don't have so much time anymore. I just wanted to demonstrate to you here that essentially we see exactly the same happening if you use 2 micrometer driving wavelengths, which gives us this atomic resolution process where I showed you the 5 picometer resolution before. And then we did lots of molecular frame measurements at 2 micrometer. This is data I want to jump over. And then we essentially, I wanted to very quickly then at least show you that we can do very similar experiment on this indole molecule, which is really, you know, part of proteins there. And so what we do in this molecule, or what we investigate, is really what happens after UV excitation. Because
you have 2 minutes.
Thank you. Because this is what really happens in biology, is that this chromophore absorbs UV radiation in our body, or in our skins. And so we did a very first ion imaging experiment again, where we could unravel all these dynamics. And I quickly jump over this, sorry for that. But we could essentially all disentangle that. And we could see how these processes happen, and how actually the water protects the molecule from falling apart, which it otherwise does. But what I really want to show you is just that we can do beat measurements, well, in a way on the dynamics here, and I can only show you t equals 0 and t equals infinity, because this is not a pump probe experiment. This is doing the experiment on indole water and on indole. But we are working on this time-resolved measurement. And what you see here is that I wanted to show you that these 2 structures are very different. So we have, for instance, all these shark-like structures in here. So there's some hope that we can really use laser-induced electron diffraction to see this nuclear dynamics. And then I already hinted at the fact that this is all very difficult. And then maybe in view of time, I really just show very briefly that we can, or we just recently developed our semi-classical simulation framework to handle such molecules. And what we do here is really that we calculate initial photoelectron density and phase using ADK, barrier suppression regime extensions, and plane wave phases. I mean, some of you are here in the audience who developed all this. Then we do a semi-classical propagation, and that's one point I wanted to make, because we do a semi-classical propagation of these electrons in the combined laser and molecular field. And the approach we take is that at far distances, we describe this as the laser field plus a multipole expansion description of the molecular potential, or the molecular field. But once we get close to the molecule, we actually use a quantum chemically accurate. So this is really a quantum chemically calculated potential, or the field here already, in which you then propagate these electrons. And the one problem you always have this is, of course, the Coulomb funnels at the nuclei. And there my student Jos Wiese had this very smart idea that once we get very close to the nuclei, and very close is so close to the nuclei that the laser field is really here, the laser field is at 10 to minus 2 atomic units, so it's really like 2 to 3 orders of magnitude weaker than the field by the molecule. Then we simply propagate this electron on a classical Kepler orbit from the sphere back to the other side of the sphere, and then we go back to the molecular potential propagation. So there, in that way, we really have a very accurate consideration of the quantum chemical molecular potential, and in all this propagate this, and then we essentially construct the asymptotic wave function. And with this, I should stop here. I thank you very much for your attention. I leave the summary just up here and look forward to your questions.
Thank you so much, Jochen, for the presentation. It was full of new things. And so unfortunately, the time, of course, led us to rush a little bit. And so the floor is open for questions. So I hopefully see some questions coming. So thank you for, in the meanwhile, I can thank you for the re-explanation about risk-adapted electrons. And maybe I can actually start with, again, something that I was not familiar with this molecular contrast ratio that you showed actually and the modulation that actually tells us is also the sensitive observable on the nuclear dynamics as far as I understood. Can you explain a little bit more about this parameter? Because I'm not familiar, just if you can't recall it, since it was
the molecular contrast factor, is that what you're asking about?
Yes, thank you.
I should actually see that I share my screen again. So this is what you're talking about, as I assume.
Yes, exactly.
And
explain me again how I can read this parameter.
Yeah, I do. So essentially, I mean, I just go back here quickly. So, oops, sorry. So this is measured photoelectron momentum distribution on my 2D detector. On the right, I have then a 3D invertible transformed version. And then I can really, I know that on this ring, the laser vector potential is the center of this ring. And so along this ring, I always have electrons with the same rescattering momentum.
Yeah.
And this gives me this differential cross-section, angularly differential cross-section of my experiment. And this is, and I didn't put this in because I assumed Kasper explained it, and he also did, so this is essentially all scattering intensity from the molecule. And that's to a very large extent, really, it's just the scattering of the 3 atoms without interference from the molecule. That's really the largest contribution, because we're essentially on the 0 order of the differential scattering there. But of course, on top of that, you have interference terms between the different molecules. And that's really what we're interested in. And that's what I've plotted here. This is really just these interference terms. Now the question is, how do I get there? Really, how I get there is, in this case, is that we know that this is a 5th order polynomial, or in a smooth decay in this differential cross section, and I can just subtract this. So really, what I did here is I assumed, or I fitted a polynomial to their atomic form factors, and subtracted this from the differential cross section, and that's what I get here as a molecular contrast factor. And it's a scattering intensity minus this atomic scattering intensity, which I somehow have to approximate, because I don't know. In X-ray diffraction, we very often use just the known atomic cross sections and pre-calculate it at this low electron energies here. That's a little tough, but you just subtract this out using an approximate function, and then what remains is this molecular interference term in the scattering, and that's what you then analyze.
I see. Thank you so much for the clarification. I don't see any question popping out in the Q&A app. Also because I think it's actually, there is a short time there are only 4 minutes, and then the poster session will start. So I will actually recommend everybody to participate, since it's the last poster session of the Autochem conference. So if you want to actually participate, I suggest to contact each poster author. And moreover, in overlap with the poster session, there is also the Meet the Speakers, where all the speakers actually result to be available, except Janaky. And I would like actually to take the occasion to thank all the speakers of this afternoon session, and just remind you that tomorrow morning at 9 there will be the last day of the conference, so everything will be on live again at 9 o'clock. So with that, I would like to thank you everybody again for the contribution, for your attention, and the very nice discussion. And I can say goodbye to everybody and have a nice evening.